In this video, we finish up section 3.6, and the first thing I'm going to start with is the definition of absolute error. So the absolute error is defined to be the absolute value of the difference between the approximation, right, with the numerical integration technique, whether that's Riemann sums or trapezoid rule or midpoint rule or Simpsons rule, and the actual value of the definite integral. Right, so for an example, remember from the very first video on 3.6, we did this example where we integrated from 0 to 1 x squared dx, and we split that up into 4 trapezoids, and our answer was 11 over 32, which was approximately 0.34. And when we do this definite integral out using antiderivatives to get the actual area, right, we end up with 1/3 minus 0, which is just 1/3, or, right, we know that's 0.33 repeating. So then the absolute error is the absolute value of the actual integral, or the actual area, minus T4 in this case, right? So this is the value of the definite integral, right, or the actual area under the curve. So for us, we got 1/3, or 0.33 minus 0.34. So then we end up with 0.01, which is a really small error. So we see that trapezoid rule works really well, even when we only have 4 trapezoids. And then the other thing I wanted to talk about for in terms of the trapezoid rule is this theorem that we have about concavity and midpoint and trapezoid rule. So if your function f of x is concave up, then the midpoint rule will be an underestimate. Meanwhile, the trapezoid rule is an overestimate. And if we actually graph this last example, if we graph x squared, we can see this here at play. Right, so from 0 to 1, it's concave up. And when we draw trapezoids, right, let's just split this up into 4 trapezoids, right? Since the right point is higher, then when we connect these, there's gonna be, right, a little bit of space above, giving us, right, an overestimate, which we saw here that the T4 that we got was greater than, right, the actual area, which was 1/3. So we know that's true. And then the opposite happens when it's concave down. Right, in that case, the midpoint rule is an overestimate, and the trapezoid rule is an underestimate. Right, and the absolute error works the same for all of the numerical integration techniques. Right, for another example, just to do it with Simpsons rule, right, we did in the last video from 0 to 1 of x cubed to the integral, right? So if we did that using the power rule, we would add 1 to the exponent, divide by the new exponent, and then we'd get 1/4 minus 0 is 1/4. And then from our approximation S2, we also got 1/4. So the absolute error is 1/4 minus 1/4, or right, there's no error. This was a perfect approximation. So Simpson's rule is pretty much the most accurate numerical integration technique that we have. Alrighty, thank you.